Hi everyone, my name is Rahav Kathori, and this is my lab 3 for physics, the black hole lab. So here's my introduction. So the purpose of the lab in part 1 was to find the mass of a black hole using a computational model that accounts for the gravitational interactions between a star of known mass and the given black hole. While in part 2, we have to find the initial velocity needed for a spaceship to get close enough to the black hole without actually being trapped in the system. So I have a quick preview of my results listed below. I found the mass of the black hole to be 9.88 times 10 to the power of 33 kilograms, and the initial velocity of the spaceship to be negative 2.637 times 10 to the power of 7 for my x component, while my y component was 2.84 times 10 to the power of 6. And I'd also like to reiterate my systems and surroundings in part 1. The star was a system, the black hole was a surrounding, while in part 2, the planet and the spaceship were the system, while the black hole and spaceship/planet were the surrounding. Um, Also, I have my initial conditions listed below. The initial conditions included the mass of the star, mass of the planet, mass of the spaceship, and the change in time, which we were all given. Here, I have a quick introduction into the fundamental principles that persisted throughout this experiment. So Newton's second law, which states that the net force of an object is equal to the change in momentum over time. This formula actually serves as the basis for the velocity update and position update formulas as well, which I have listed below right here. Additionally, the gravitational force formula played a pivotal part in this experiment, which describes the gravitational force of an object on another object. I have the formula here along with the gravitational constant right to its right. Another fundamental principle that existed throughout this experiment was the parallel and perpendicular components for the net force. The parallel component, or p hat, is related to the speed of an object, which is directly related to speeding up and speeding down, of course, while the perpendicular component and hat is related to the change in the direction of an object. And here I have a few theories that pretty much elucidate the parallel and perpendicular components further. Here, I included an image of my computational code for part 1, which includes the gravitational constant, the star of the mass of the star, and delta t, along with t being equal set to 0. And here I have my overall computational code set up for the entirety of part 1, which includes the rate, which includes how fast the simulation is actually running, along with everything else. You can pause and take a look if you'd like. And here I have the results and discussion for part 1 of my experiment. So I found the magnitude of the net force at final to be 8.924 times 10 to the power of 28. And I found the magnitude of the parallel component of net force at final to be 3.418 times 10 to the power of 27, while the magnitude of the perpendicular component was 9.59 times 10 to the power of 28. And overall, the mass of the black hole, as stated earlier, was 9.88 times 10 to the power of 23. And the mass of the black hole was actually found through multiple iterations. Thus, there were many values for the mass of the black hole, and an overall average was taken after running this simulation multiple times. So there are many sources of error that actually persist in this experiment as well. Like I just mentioned, the multiple iterations allows for some error, along with the rounding errors and the fact that many averages were taken as mentioned. Now I'd like to go into the computational code for the second part of my experiment. Here I have the listed constants along with the different initial conditions listed below. You can pause and take a look if you'd like. Along with the computational code setup, same thing as that. The rate was here mentioned, along with the net force, which I added these lines here. You can pause and take a look if you'd like to see my code further as well. Here I have the results and discussion portion for my part 2. I found the initial velocity of the spaceship to be this value, these values right here. And spatially, as for a conceptual understanding, the spaceship is getting as close as possible to the black hole before not being able to get any closer, leading it to be kicked out of this from the surrounding. Thus, it is moving up to the left and up while experiencing its maximum gravitational force. And I have an image here that shows this simulation in GlowScript. And the overall ship ends up here at this value away from the event horizon. So the same or sources of error persist here as they did in part 1 for the experiment, as we are taking multiple iterations, along with the rounding and estimation errors that result from the multiple iterations, and the fact that the gravitational constant is being rounded instead of using the entire number. Finally, what does this mean in the larger scope of things? So how do the velocity and the rate of change of momentum for the components relate? The velocity is actually going to be equal to the rate of change of the momentum, and the parallel and perpendicular components of the net force are also equal to the rate of change of the momentum. And I have this here listed below, so you can take a look, which kind of just correlates the components of the net force together. So what if the initial velocity So what initial velocity would we need to enter into an orbit around the actual black hole? So the initial velocity, I found that would need to increase in the y magnitude while staying the same or decreasing in the x magnitude. This would allow for the spaceship to increase in a vertical manner, allowing for a sufficient initial trajectory when it comes to entering the orbit. And I found this new initial velocity value to be this. Thank you so much for your time.